We're now going to look at mock term test 2. The focus on this is dimension and transformation. So week 4, 5, 6, 7. None of the theorems or definitions from 8, but there might be examples from the earlier units that show up in week 8 because you know them from past units. So our first question, we have let alpha be a set or be the set 1x, x squared, and this is a basis of polynomials of degree at most 2, where the coefficients are real numbers, and beta be the standard basis for R2. The standard basis means that beta equals the set E1, E2. And remember, E1 is 1, 0, and E2 is 0, 2. Okay. Now we have a linear map. And a linear map is a linear function, linear transformation, linear operator. All those words mean linear transformation, which goes from our polynomials of degree at most 2 to R2. And the function that they have is a polynomial that T maps P of X to P1, P2. And this should be a lowercase p for P2. Show that T is a linear transformation. So to show, when we look at showing T is a linear transformation, we might get a little scared because this is P1 and P2, and what does that mean? But remember, if P of X is in P2R, okay, so T of P of X is simply P of 1, P of 2, right? Now, if we consider just a generic vector, that would be ax squared plus bx plus c. So if we're applying t to this function, this would equal a1 squared plus b times 1 plus c, a2 squared plus b times 2 plus c, which equals a plus b plus c, 4a plus 2b plus c. And that would be my output. Okay. Now, we don't have to do generic elements like this to prove it's linear. It's helpful when considering the matrix representation, but for now, all we have to do is consider two polynomials and a constant, because to show something is a linear transformation, we show that TCA or TCU plus V equals TC of U plus T of V. This is our goal. Okay. So with these type of problems, I like to do a left-hand side, right-hand side. I'm going to let P or let C be an element of, and here, because it's R, my field is the real numbers. So it's going to be C is an element of R, and X and Y. And instead of doing X and Y, I'm going to do P and Q are elements of polynomials 2 in R. Now, my left-hand side is going to be T of C, P plus Q. I did not mean to put an arrow there, Q of X. Okay. Remember, the U, CU plus V, because these are functions, CU plus V is CP plus Q of X. That is the added function. I'm considering the function CP plus U, or CP plus Q. So when I'm looking at what T does to this, it's CP plus Q of X equals CP plus Q of 1, CP plus Q of 2. And now here, I'm going to use my definitions, and this is by definition of T. I'm now going to use my definition of function addition and function scaling here. So it equals CP of X, or of 1, plus Q of 1, comma, CP of 2 plus Q of 2. Right? Now here, it'd be nice to split my Q's and my CP. So this gives me CP of 1, comma, CP of 2 plus q of 1 plus q of 2. This was by definition of function addition, and this is by definition of vector addition. Now, it's nice that I have a scalar here. I can factor that out to give me c, p of 1, p of 2, plus q of 1, plus, or q of 1, comma, q of 2. And now here, it might not be as easy to see. This is let's complete our justification by definition of scaling vectors. And this is equal to Cp of t applied to p of x plus t applied to q of x by definition of t. And we have that our left-hand side equals our right-hand side. Thus, t is a linear transformation. Not linear independent, linear transformation. Or in this case, because they used the word linear map, you might want to write linear map. Okay. Next, we want to write the matrix T alpha beta. Okay. So to do this, what I'm going to do is I'm going to look at what T applied to 1 gives me, T applied to x gives me, and T applied to x squared gives me. So this here, T applied to 1 would be 1, 1. Because if I look at if f of x equals 1, then f of 1 equals 1 and f of 2 equals 1. Sometimes it's easier to write this in your head and then do, okay, what's f of 1, what's f of 2? Next we have g of x equaling x. Then g of 1 equals 1 and g of 2 equals 2. So we have the vector 1, 2. Finally, we have the vector, my function h of x equals x squared. So h of 1 equals 1 squared, which equals 1, and h of 2 equals 2 squared, which equals 4. So I get 1, 4. Now, I have to write each of these outputs using the basis beta. So this was going through alpha. And now I have to express these using beta. So this is 1, 0 plus 0, 1, which equals 1 E1 plus 1 E2. Because the basis beta equals the set E1, E2. Here, in a similar argument, we get that it's 1 E1 plus 2 E2. And here we get that it's 1 E1 plus 4 E2. Combining these, I can get T alpha beta. And my first column comes from my coefficients from my first row, 1, 1. My second column comes the coefficients from my second row, 1, 2. And my third column comes the coefficients from T applied to the third vector, which is 1, 4. And that's my matrix representation. And the next question, we suppose W1 and W2 are subspaces of a finite dimensional real vector space. So here, the keywords I see here are finite dimensional and real. Because it's real, R is my field. In the question, they tell you what the field is. It's R, finite dimension. This means that the dimension of V equals N. And instantly, there's a few things that I have. One of those things is that V has a basis. And this basis is finite number of elements. It is linearly independent, and it spans V. So whenever I hear finite dimensional real vector space, to me, that tells me a bunch of information right away, okay? And I know that W1 and W2 are subspaces of it. Now, here, It tells us that we may assume without proof that if W is a subspace of V, then W is finite dimensional. So in this theorem that we're given, this also tells me that the dimension of W equals K. This is finite number of elements. It is linearly independent and it spans W. The first question says that prove the dimension of W1 intersection W2 is less than or equal to the dimension of W1 and the dimension of W2. Now, in order to do this, I have to show first, I need to show W1 intersect W2 is a subspace. Because if it's not a subspace, then dimension doesn't make any sense. I need to get that intersection is a subspace. So to do this, I'm going to let X, Y be an element of W1 union W2 and C be an element of the real numbers. And I want to show that Cx plus Y is an element of W1 intersect W2. So as X and Y are in W1, then Cx plus Y is in W1 as W1 is a subspace. Likewise, as X and Y are in W2, Cx plus Y is in W2 as W2 is a subspace. As Cx plus Y is in W1 and Cx plus Y is in W2, Cx plus Y is in W1 intersect W2. Okay, thus it is closed. I have not shown non-empty. I've shown closure, but I have not shown empty. I need to show that it's non-empty. So non-empty is missing. To do this, 0 is in W1 and 0 is in W2 as W1 and W2 are subspaces. Thus, 0 is in W1 intersect W2. Therefore, W1 intersect W2 is non-empty. So at this point, I have shown that W1 intersects W2 is a subspace. Because of this, I'm allowed to conclude that it has a basis. I'm allowed to conclude that W1 has a basis and W2 has a basis. Okay, so we're going to let alpha be a basis for W1 intersect W2. Let beta be a basis for W1. Let gamma be a basis for W2. Now, as alpha is a subset of W1 intersect W2, alpha is a subset of W1, and alpha is a subset of W2. Now that we have this, alpha is a linearly independent subset of W1, and beta is a spanning set of W1. Thus, the cardinality of alpha is less than or equal to the cardinality of beta, i.e., that is to say, the dimension of W1 intersect W2 is less than or equal to the dimension of W1 as the dimension of W1 intersect W2 equals the cardinality of alpha, and the dimension of W1 equals the cardinality of beta. Left as exercise. So I'm going to leave the second one as an exercise. A similar argument, which I encourage you to do together, shows, or I encourage you to do on your own, shows that the cardinality of alpha is less than or equal to the cardinality of gamma, i.e. the dimension of W1 intersect W2 is less than or equal to the dimension of W2. Whew, a lot of work. Overall, there's two key ideas here. First, show W1 intersect W2 is a subspace. Two, dimension bound theorem. Lovely. There's a little bit here of the intersection of two sets is a subset of each individual set. That is a property we used here, but if you wanted to, let X be in W1 intersect W2, then X is in W1 and X is in W2 by definition. It's not terribly difficult, but you could go through that proof as well. The next one is more of a search. See if you can come up with one. So here we have, suppose W1 and W2 are both two-dimensional subspaces of R4. Turns out that the dimension of the intersection could be equal to 0, 1, 2, provide an example of each case. I like to keep this easy. So when it says the dimension is 0, this means that the intersection is just the 0 vector. So if I let W1 equal the span of the set containing E1 and E2, and W2 equals the span of E3 and E4, then all vectors will look like x, y, 0, 0, and these vectors will be 0, 0, or let's go wx 0, 0, 0, 0, y, z. Typically, when it's four vectors, we do wx, y, z. And now we can see that the only place where these two don't overlap is just that 0, or its dimensions 1. How would I show this? Well, let x be in the intersection of W1 intersect W2, then x equals a E1 plus b E2, and x equals c E3 plus d E4, which implies that a E1 plus b E2 equals c E3 plus d E4, which implies that a b 0, 0 equals 0, 0, c d, which implies that a equals 0, b equals 0, c equals 0, d equals 0. So x equals the 0 vector. Thus, W1 intersect W2 equals the set containing the 0 vector. Lovely. That means that this set, when you take the intersection of the two sets, you have dimension 1 or 0. Now, we want one overlap. So for one overlap, what I'm going to do is I'm going to let W1 equal, and I'm going to pick the same set, E1, E2. And W2, I just want one of them to overlap. So I'm going to be E1 and then E3. So one of them overlaps, one of them doesn't. W1 intersect W2. I want to see what this is, right? Well, let X be in W1, let X be in W1 intersect W2, then X equals AE1 plus BE2, and X equals A or C E1 plus DE2. Thus, AE1 plus BE2 equals CE1 plus DE2, E3, sorry. Well, this implies that AE1 plus, or this implies that AB 0, 0 equals CD, or C0, D0, which implies that A equals, or A minus C equals 0, B equals 0, and D equals 0. This is our system of equations. Well, now what we can have is we have one free variable. Let S be an element of the reals, then A equals S equals C equals S. Here, it might be tempting to say, well, my basis vector is 1, 0, 1, 0, but that's not the case. What it's saying is it's saying that the leading term of either of these vectors can be any number. They just simply have to be the same number, which means that if this is true, then x equals here a times 1, 0, 0, 0, which equals c times 1, 0, 0, 0. If we phrase it this way, it's a lot easier to see. So x or W1 intersect W2 equals the span of the set 1, 0, 0, 0. So the dimension is 1. Now for W1 equals the set E1, E2, and W2 equaling the set E1, E2, you can show that this has dimension 2, but I'm going to leave that as an exercise for you to go through.